Good morning. Welcome back to the second lecture of ECE484, Fall 2021. So we're going to continue where we left off, but just so you know, at the start of every class, I'd like to do a summary of what we talked about in the previous class, just to make sure that we're all on the same page. Okay, so what did we do in lecture number 1? Well, so we went over the course administration, so the course outline. All that information is available on the course website, Learn. I do want to mention one thing, a couple of things actually. It's a very fluid situation at the university, it seems. First, if you do want to switch from in-person, so in other words, if you're in a blended section and you want to switch to online, you have a deadline of September 21st to do it. This is what I've been told, so please be aware of that. Also be aware that if you switch just, say that if you want to switch just the lab, well, what the registrar is going to do is it's going to switch you all to online, right? So you will no longer be in the technically in the in-person lecture section. Now, having said that, it was pointed out to me yesterday that those slides that the university provided about occupancy limits conflicted with what we were doing for the lab and so on. And so we received an email this morning saying that the Faculty of Engineering has removed occupancy limits for teaching spaces. So I'm going to talk to some people this afternoon, but stay tuned. It might mean some changes to what I said yesterday in terms of number of people in the labs and so on. Okay, so that's admin stuff. We went over classroom expectations, kind of mandatory stuff. Main thing being, if you're sick, stay home, wear a mask at university. Okay. So then we started going over an introductory example, and the example was meant to sort of at least get some of the jargon of your third-year control course in your mind, and also give you some of the themes of what we're going to be doing in this course, namely designing controllers and then implementing them on computers. And trying to be a bit more principled in the way we do that, right? We're trying to make sure that when we do this implementation, things work in a reasonably well way. Okay, so we had the cart. There was this simple cart example where we wanted to control its position, one-dimensional motion. And we decided to use proportional control, and we talked about all the nice properties that the closed loop system would have if we used such a proportional control. Okay, and then we started talking about the implementation. How do you implement this when you have, analog to digital conversion hardware, similarly digital to analog conversion hardware, and a microprocessor which is implementing the actual control law, the feedback control law. Okay, and basically we left off with this idea that the program running on the computer is going to basically cycle through the following steps. So step 1 is going to be sense, right? So read the sampled values of Y, the position of the cart, and R, the desired position or the commanded position of the cart. So update those values. Compute the controller, the control signal. In this case, it's very trivial. It was just a gain, Kp, times the difference between the sampled values of the command or the reference and the output. And then lastly, to actually do something, to actually cause the cart's motion to be affected by this computation, we have to actuate the cart. And that, step 3, actuate. And we have to convert this discrete time signal, U of Kt, so remember, capital T is the sampling period, into a continuous voltage. So we want to convert that into a voltage. And there's lots of ways to do that. There's pulse width modulation. There's other types of D to A hardware. But the simplest method is to simply hold the value of UKT, so this computation, this value that we've computed, constant over a sample period. Okay? And that's what I'm kind of illustrating in this picture. So on the left, you have kind of a representative diagram of what the discrete time signal might look like. Right? So notice in a discrete time case, you can write it as a function of Kt as the independent variable, but you can also write it as a function of K, right? So at K equal to 0, we computed a value of 0. When K was equal to 1, we computed some positive value. When K was equal to 2, we computed some other positive value, and so on, okay? And so what our simple model of a D to A is going to do is going to hold those values constant over a period. And so we're going to hold. And when we do that, we now get a continuous time signal here on the right. So notice now that the independent variable is time, and now our control signal is continuous. It's defined, it's a continuous time signal. It's defined for all values of t. And so again, the hold is going to hold the value constant over one period, It's going to switch to the new value, hold it constant, switch to the new value, hold it constant, switch to the new value, whoops, hold it constant, switch to the new value, hold it constant. Too much coffee, a bit jittery. Okay, and then if you wanted to write down an equation describing that, we would say that u of t is going to be equal to the computed value u of k over one sample period. And that's what that explains over there. Okay, and so again, the basic idea of this feedback loop, like any control system, is the following sequence of events. Sense, compute, actuate, right? So read the sensors, update your control value, and then actually do something for the physical system, and then repeat that. Right? That's the central. That idea right there is the central idea in real-time control. Okay, so let's now simulate that system and kind of see what happens when we play around with the sampling period. So I'm going to show some MATLAB simulations, and these simulations are available on the course website. Okay, so let's see here. All right. So I think we're good there, MATLAB. Okay, so I'm going to just kind of describe the code here, and then, again, you should play around with it on your own. So this is just our motivating example, the cart control. I'm going to simulate this system for 20 seconds. So that's this line 5 here. Hopefully you can see it reasonably well. For the first simulation, I'm going to set the sampling period to be 0.05 seconds. So relatively fast sampling, okay? And then the rest is sort of the usual stuff. So I'm going to define my plant transfer function, which we derived last class. I've got a controller, my proportional gain. I'm going to use a proportional gain of 2. Okay, so the value will be 2. There's my continuous time controller. And so what I want to do in this simulation, I want to compare a purely continuous time simulation to a simulation which actually includes the analog to digital conversion hardware and the digital to analog conversion hardware. Okay? And so what I'm going to do that is I'm going to use a GUI that MATLAB has, which you've probably used before, called Simulink. And Simulink is nice for doing this type of stuff in this course, because if in Simulink you connect a continuous time plant, so P here being our plant, the transfer function of the cart, to a discrete controller, D, it will automatically add in the A to D and the D to A. Okay? So what I'm going to do in that file is I'm going to simulate my continuous time, a purely continuous time closed loop system. I'm going to get the result. And then I'm going to simulate this diagram that I'm showing here, and I'm going to now get this mixture of continuous time and discrete time signals. And then I want to just compare the two simulations as I change the sampling period. So how often we are updating the sensors and actually updating our voltage that we're sending to the cart. Okay? Okay, so in the first simulation, the sample period was going to be small. So I would expect, if you're sampling really quickly, hopefully your intuition suggests that the continuous time system will behave very much like this system that has a mixture of continuous and discrete time signals. So let's run it. Okay. So the first figure that you're looking at here, and it may be hard to see, hopefully you can see. Let me turn off my video for a second so you can see better. The red line is the the blue line is the purely continuous time system. So that is, if you remember last class, the block diagram where the controller is a transfer function C of S, the plant is a transfer function P of S, and everything is continuous time. And that gives you the blue line here. Okay? The red line is the term we're going to use is sample data. So it has a mixture of continuous and discrete time signals. And you see it's pretty close, right? Our intuition said it would be pretty close. And indeed, there's not much difference between the two. Excuse me. So let's look at some of the other figures. So that's it. What you're seeing in this figure is step 2 of what we just talked about, right? It's the discrete time calculation. So I'm showing this stem diagram, or lollipop diagram sometimes it's called, which it shows what happens to the computed value of the control signal at each discrete time step. So notice the horizontal axis is in terms of k, right? So this is step 1, step 2, step 3, and so on. Okay? And as we said before, step 3 is to then hold this value over a period to generate a continuous time signal that gets applied to the plant. And so that is what you will see here. So this is the control signal being held constant over one sample period. And you see a little bit of jagginess here. Hopefully you can see that reasonably well. But it's pretty close to what the continuous time control signal would look like. Okay, so let's repeat that simulation, but this time let's change the sampling period. Let's do it a bit slower. So I'm going to make it 0.1. Actually, let's make it 0.2, make it a bit more exaggerated. So this is, we're only sampling 5 times per second here, right? So you can imagine that if you're doing image processing between samples, maybe you don't have the priority. The control loop does not have the priority to update its signal often enough, right? So you can only update it every 0.2 seconds. So let's see what happens. Okay. Now, in this case, if you look at the figure, the blue hasn't changed. That's the continuous time system. But now our sample data system is actually a bit worse. We're getting more overshoot. The oscillations are a bit worse. The performance is degrading, as you'd expect, right? As we increase the sample period. Okay, and then the other 2 figures are similar. I won't blow them up, but here's the held value. Here's the. Put this over here. Here you have the discrete time signal being generated by the controller, in software, and then this is the value of the control signal being held. And again, you notice that because of our sampling period is 0.2, it's only changing every 5 times per second. The value is changing 5 times per second. Okay, so you can imagine what's going to happen if we keep increasing the sample period, right? This overshoot's probably going to get worse. The oscillations are going to get worse, and in the extreme limit, when you're doing it too slow, you would expect some instability. So let's see what happens. So now I've changed the sampling period to half a second, so only updating the control signal twice per second. Okay, getting worse, but still stable. This is it's a simple example, right? We have a mass which is 1, friction is 1. So, but you can imagine for other systems, this is going to be, half a second. It would be way too slow. Okay, so let's be extreme. Let's go to a second and see what happens. Okay, now we see that things aren't converging, right? So now, if we're only updating our control signal once per second, okay, maybe arguably it's going to converge eventually, but the convergence is extremely slow. Right? And so that's what you're seeing here. Okay, so this issue of the sampling period, how do we guarantee the performance of our discrete time system? These are some of the issues we want to tackle here, right? You want to control a system using feedback control, but you want to implement it on a computer. And what we want to do in this course is sort of explicitly model the effect of that computer and try to account for it in our designs. Okay? Okay, so let's go back. Hopefully you guys can see that. Okay, great. All right, so we're going to continue. So that's our simulation. Let's continue with the lecture material. All right. Now, when you have these systems which have a mixture of continuous time and discrete time signals, there's sort of 2 main design philosophies. There's a design philosophy where you treat it as a purely continuous time system, or there's a design philosophy where you treat it as a purely discrete time system. And so what I want to talk about now is sort of where that philosophy comes from, or how we can kind of intuitively think about where those philosophies come from. Okay, so I want to draw a picture here. Okay, so what we have in this picture is sort of what that closed loop system looks like from the point of view of the cart. So let's write that down. From the viewpoint of the cart, the closed loop system appears purely continuous time. And so if you look at this picture, like the cart, what it's seeing is a continuous time signal coming into its input. The cart itself produces a continuous time signal, and it sends it back to the red box. Right? So this is what the cart sees. Right? On the other hand, if you take the point of view of the processor, it's going to see a purely discrete time signal, right? System, right? It's receiving information from the A to C and sending information to the DAC. So conversely, from the viewpoint of the processor, the closed loop system is purely discrete time. Okay, and so I'm going to then paste the picture again from the notes. Okay, so the processor sees this digital signals coming in and producing digital signals. So both of these viewpoints, we're going to try to take both these viewpoints as we go through this course. Okay, so let's wrap up this example. And say the following. In this course, we study both continuous time and discrete time systems. And in particular, what did you write in purple? I wrote what the cart sees. So that box there around the AID, analog to digital controller, and the digital to analog converter, is sort of the system that the cart is interacting with, right? So the thing coming out of that red box is the voltage, and the thing going into that red box is the position. And what I wrote in purple is what the cart, and it should be cart, let me write that again. Cart sees. Okay, so hopefully that's okay. Let me know if otherwise. So we're going to study both continuous time and discrete time systems and their interconnection. Okay? And it's the interconnections that are actually the most interesting part in some sense, right? If you have a purely continuous time system, you've seen that before. If you have a purely discrete time system, it's not that different. But when you start interconnecting them, things get interesting. So, you know, in the modern language, they would say these are cyber-physical systems, right? They would say continuous time and discrete time. Okay, and so for us, when we have a system which has a mixture of continuous time and discrete time, we're going to call that sample data. So systems with a mix of continuous time and discrete time signals or elements are called sampled data systems. Okay? And we're going to study those. Now, obviously, this course focuses on the controller design aspect, but there's lots of knowledge that goes into designing a real-time control system. And so I just want to kind of point out the big picture here in terms of what you actually need to design these systems. So to design a real-time computer control system, you need knowledge from various domains. So one requires knowledge from various domains. Okay. Sorry, my tablet is lagging here for a second, so I'm just going to change this for a second. Hopefully this works. Okay. Okay, so what are those domains that we need to know? So one is discrete time systems. Okay. And the reason for that is it doesn't matter how fast the computer runs that you're doing the control on, it's going to operate in discrete time, right? It has a clock cycle. It's going to run every so often. So no matter how fast the CPU runs, it operates in discrete time. Okay? And so in this course, we're definitely going to look at discrete time systems, and we're going to review discrete time systems. We also need to know something about control systems, right? If you're going to be designing feedback controllers, you need to know a little bit about control systems, and so right? And so some of the ideas that we're going to be doing in this course, we're going to be approximating continuous time controllers. Sorry, I've got a technical issue. I'm just going to try and fix my screen for a second. So bear with me for 1 second. Give me 1 second. I'm just going to be right back. Okay, we should be better now. Okay, so control systems. You also need to know about control systems. You need to approximate. We're going to learn how to approximate continuous time controllers. What else? We want to design. We're also going to have to know design discrete time controllers that have no continuous time equivalent, right? So we're going to be able to design things in discrete time that you can't do actually in continuous time. And we want to get good behavior between sample periods. Okay, and those are topics that we're going to cover in this course, all three of those topics. Third thing you sort of need to know a little bit about is hardware, of course. So, choosing sampling rates, the hardware that you're using for digital to analog conversion, and so on. So sampling rates, sampling rate selection. We'll talk about that in this course. What we won't talk so much about is sort of choosing the hardware. Right? We're going to assume that that's sort of fixed. In fact, we're going to use a very simple model for our A to D and our D to A. Dealing with quantization. Right? So that simply is about the precision when you sample something. How precise is that sample? Right? Computers have finite precision, and so how do you deal with that? Anti-aliasing filters. If you look at the appendix of Chapter 1, we talk about, typically when you have an analog to digital conversion block, you want to have a filter in front of it to deal with the effects of sampling high frequency noise. Okay? And finally, you need to know a little bit about real-time aspects, right? So real-time systems. So scheduling of the operating system, right? Typically the computer is not just doing control, it's doing other things like data acquisition, maybe updating information for the human-machine interface. So it's doing other things, right? So it has to schedule time to update those control signals. So scheduling plays a role. So thread priorities. Timing analysis, etc. Okay? So the point being that it's sort of an interdisciplinary topic that covers a lot of aspects of engineering. This course, for the most part, we will focus on 1 and 2, with a little bit on number 3. And in terms of number 4, I might ask you a couple of questions in the problem sets, but we really won't talk too much about that aspect of these systems. Okay, so let's keep going. So what I'm going to now do is I'm going to go through sections 1.3, 1.4, and 1.5 of the notes, just to remind you, when I say continuous time system, discrete time system, sample data system, what exactly do I mean? So continuous time control systems. And so what I'm going to do is I'm going to just grab the figure that's in the course notes. Okay, so this is a diagram which you've probably seen many times in your third year course. You may have forgotten about it, but this is our continuous time control system. So in this figure, there are systems and signals. So let's go through what's in this diagram. So in this diagram, there are systems. In particular, there's the block with the P symbol, so P of S. is typically what's called the plant. Right? So that's the system you're trying to control. That's kind of the fixed part, right? It's sort of based on the hardware you're trying to control. That plant is fixed. C of S is the controller transfer function. That's the non-fixed part of the diagram. That's the part we get to choose, right? The mechanism for which we make decisions to actuate the plant. Okay. There are also signals, of course, in this diagram. Okay, and I'm just going to go through them to remind you of what they all are. So R is the reference input, okay, or sometimes called the command input. It represents the desired value of the output. D is a disturbance input. So it's some input coming into your plant or into your loop that you have no control over. Right? It's something that is just out there and is affecting your control system. So in the case of the cart, that could be wind, for example, affecting the motion of the cart. It could be inclination of the road. Instead of being flat, maybe it's inclined. And so that's what D is. It's an external signal which you have no control over. Okay. E is the tracking error. Right? So E is the difference between the reference input and the plant output. And a good control system will drive that to 0. Right? A cruise control system, when you set it on your car, you expect that it's going to maintain the desired speed. The difference between the actual speed of the car and the desired speed of the car should be 0. Right? That's what you would expect from a good cruise control system. Or if you're into drones and stuff, when you have a drone, you buy a drone and you have it floating in the air, you expect that if you don't command the thing to move, it should stay put. It should stay at a fixed height if there's a good control system on the drone. Okay, U is the plant input, and Y is the plant output. Okay, and I just want to mention, or kind of reiterate, that of these signals, when you look at this block diagram, once you've designed the controller and once you hook it up in this way, the only external influences on this system are coming through the reference and the disturbance. So these are typically called exo signals. Exo meaning from the outside world, right? So those are the independent inputs after you've closed the loop. Once you've closed the loop, the inputs to the closed loop system are the reference and the disturbance. Everything else is dependent, right? E, U, and Y are dependent signals on R and D. Okay, so typical specifications, which you would have seen before, but remind you. So typical control design. Specifications. Well, certainly stability. We mentioned that briefly last class. Okay. Typically, you want good transient performance, right? So if I command this cart to go to a particular position, I don't want it to oscillate wildly before it eventually settles down. So good transient performance. And robustness to plant model uncertainty. Right, so you have this model for the plant, P of S. It's an approximation. Every model is an approximation. No model is perfect. So there's some uncertainty, right, about what is modeled and what is not modeled. And so we would like our feedback control system to be able to deal with the fact that we probably have a pretty crude approximation of what the plant actually is. And disturbances. Right, so if the gust of wind comes, our cart shouldn't all of a sudden be so fragile. The cart control system shouldn't be so fragile that it doesn't work anymore. And finally, good steady state performance. And by that I mean typically that in the long run, if you let your automatic system run for a while, it will achieve, Y will actually get to the desired value, R. So typically what we mean is tracking. i.e. Y of t approaches R of t as t gets large. Okay. And so those are sort of the typical specifications that you would have seen likely in a previous control course. And we'll go over some of those things in chapter 2. Okay, so that's a continuous time system. And of course, you can imagine that we could do the exact same thing, but where now everything is in discrete time. All the systems are discrete time systems, and all the signals are discrete time systems. And so that's what we're going to talk about next. But it's going to be, what you're going to see, and maybe what you can get out of it, is that the discussion is going to very much mirror what we just talked about for continuous time systems. So 1.4. Discrete time control systems. All right. And so once again, I'll just grab the picture from the notes. You can take a look there. So what the picture is. Okay, so there's our discrete time control system, and I emphasize that it kind of looks the same, right? I mean, if you didn't have the dashed lines and the Zs instead of the Ss, you would say, well, it's the same thing. And I think that's one of the things you should take away, that discrete time control systems are very much like continuous time control systems. Okay, so let's do the same sort of thing. So the systems, well, there's a plant, of course, again. So P of Z is the plant transfer function using Z transforms. So the Z transform is to discrete time as the Laplace transform is to continuous time. This is an input-output model of an underlying system which is only defined at discrete instances. Underlying system that is only defined at discrete time instances. Okay, and in the discrete time domain, what it's really modeling is a difference equation as opposed to a differential equation. So represents a difference equation. So let's do a little mini example here to see what that looks like. So for example, I'll do it here. Suppose that the plant, which produces the output y, is just a simple averaging, right? A moving average. So example, y of k takes the input at time k, as well as plus the input at the previous step, u of k minus 1, and then takes their average, right? So you might do this, for example, if you're doing filtering, right? If you've got a sensor which is giving you noisy data, you say, okay, well, it's kind of jittery, maybe I just average the two measurements. That's going to be the way I deal with the sensor noise. So there's a 2-point moving average. Okay, so that system beats a linear difference equation, and it has a input-output or transfer function model as well, and you obtain that by taking Z transforms as opposed to Laplace transforms, again with assuming zero initial conditions. So what this looks like if you go to the Z domain. So the Z transform of y of k is y of z. The Z transform of u of k is u of z. And then in the Z domain, going back in time by one index is equivalent to multiplying by 1 over z. So I'm going to write that as Z inverse u of z. Okay? And then now you do the same thing we did in the first lecture, rearrange, and you're going to get your transfer function. So in this case, our transfer function is z 1/2 times z plus 1 over z. Okay? So that's what the plant is, right? It's an underlying system which is modeled by a linear difference equation. Okay, but the rest of the stuff is sort of the same, and the interpretations would be the same. So let me continue. I'll do it down here. So we're still talking about systems, d of z. Is the controller. Right? And so what we want to be able to do is design d of z. Right? So d of z, at the end of the day, we're going to be generating a difference equation that it's convenient often to just write it as a transfer function. But when you implement it on a computer, of course, you're going to implement it as a difference equation. Right? So if you've managed to design d of z and you want to implement it, you convert it to a difference equation, or probably more commonly these days, a state space model, and then you convert it into, that's the thing that runs on the computer. That's the algorithm that runs on the computer. Okay, and then the signals are similar to before. Same interpretation. So R is the reference input. D is a disturbance. Once again, those are, in closed loop, those are the independent signals, the things that determine all the other signals in the loop. E is the tracking error. U is plant input. And Y, plant output. All right, so that's all the same as before. Okay, and so in this course, we will, by the end of this course, if I give you a P of Z, you will be able to design controllers D of Z that meet certain specifications in discrete time. Okay. And finally, like I said, the most interesting behaviors, I guess, is when you kind of a mixture of both. When you have the continuous time system, a discrete time system, and they're mixed together. And that's these sample data systems. And again, I will grab the picture from the notes. And so what do we have in this picture, right? So let's go through it a little bit. We have our continuous time plant, like the cart. right? It has input u of t, output y of t. We have our disturbance. I've drawn just one disturbance here in continuous time. And so basically you can think of everything on this side as being the physical world, right? So the continuous time world. And then you can think of everything on this side as being the algorithm running on the embedded processor, the computer, okay? And so the system that you're trying to control operates in continuous time, but the controller itself operates in discrete time, okay? And it's these interface elements that make the whole thing interesting in some sense, or different than what you've seen before, okay? And so that's the kind of system we're going to study in this course. And so what we're going to want to do is, if I give you, the design problem is going to be, if I give you continuous time specifications for the physical system, design a discrete time controller to meet those specifications. So the design problem is, let's keep that in the image. So our design problem is given continuous time specs, set of continuous time specifications, and a plant model. Right? We already talked about what those continuous time specifications might look like in the continuous section. Design d of z so a digital controller, so that the closed loop system meets the specs. Right? And so that's the main, I would say, problem that we're going to look at in this course. Okay? And in terms of approaches, we're going to take two different approaches. And they're kind of the standard approaches. So there are two main approaches. The first is called, the jargon is emulation. And roughly speaking, in emulation, you do kind of what you did in your third year course. You ignore the interface elements. You ignore the A to D. You ignore the D to A. Design a continuous time controller, C of S, and then you discretize to implement. So in the emulation approach, you treat the sample data system as a continuous time system. And design C of S, right, the continuous time controller. And then you approximate. C of S with a discrete time controller. D of Z. Okay. And I've got a minute left here. I'm almost done. The advantage of this is that it uses your known design techniques, right? All the stuff you've learned before, you just keep using it, and you just need to learn how to approximate. So the advantage uses known design techniques, plus some that you maybe don't know that we're going to go over in this course, right? So we'll learn some continuous time design techniques, and then we can apply them to this problem. And so that's nice. The disadvantage is that approximation, when you go from continuous time to discrete time, as we saw in the simulation today, it doesn't guarantee performance. So let me just write this last point and we'll stop. requires a small sampling period. So it only works well for fast sampling. Okay, so I'm going to stop there. We will meet on Tuesday, and we'll talk about the other design method, and then we'll start doing the review of third year control. Okay, I will hang around for a couple of minutes, but otherwise I will see you on Tuesday, and have a good weekend. Okay, everyone? So the question is, what is considered fast sampling? We'll definitely go over that as the course goes on, but essentially you look at the closed loop bandwidth of the system, and you want it to be roughly 5 times that value. Okay, so you look at the bandwidth of the control system, you want to sample about 5 times above that, if possible. Okay, and this will be discussed when we discuss emulation.